We've talked about how to find the transpose of a matrix, whether it's a square matrix or a rectangular matrix, and we looked at how to find the determinant of both a matrix and its transpose and said that those two things were equal to one another. So now we want to talk about the transposes of the product of matrices, the sum of matrices, and the transpose of an inverse matrix. So the first thing we want to start with, of course, is products. And we just have this simple but very important rule that we'll use a lot going forward, which is that if we take the product of two matrices, so let's just say we have the matrices A and B, and we take their product, of course that product is going to look like this, A times B. This product is going to be some resulting matrix, so AB itself is a matrix. So if we want to take its transpose, then the transpose of that matrix we could just write as AB transpose, because we don't know what AB looks like yet. We could just take that matrix and transpose it. Well, as it turns out, this is equal to the transpose of the individual matrices, but with the opposite order for the multiplication. So this is not going to turn into A transpose times B transpose. It's specifically going to turn into B transpose times A transpose. And remember that order matters because matrix multiplication is not commutative. So B transpose multiplied by A transpose is not going to be the same thing as A transpose multiplied by B transpose. So this switching of the order here is really important. And this formula is something, like I said, that we'll use over and over, where we have the transpose of a product and we break it down into separate transposes, or we have these separate transposes and we sort of consolidate them into one transpose like this. So we'll use this formula going back and forth both ways. Now, if we want to prove this to ourselves, we could maybe say that A is equal to, let's say, 2, negative 1, 1, 0. And maybe we'll say that B is equal to 3, 0, 1, 1. If we want to prove to ourselves that this equation is true, we could find the value of the left side and then find the value of the right side and make sure that they're equal to each other. So the left side would be, we just multiply A by B. So if we multiply A by B, we're going to get another 2 by 2 matrix. And that 2 by 2 matrix is going to be 2 times 3 is 6, plus negative 1 times 1 is a negative 1. We'll get 2 times 0 is 0, plus negative 1 times a 1 is a negative 1. And then here we'll get 1 times 3 is 3, plus 0 times 1 is 0, and then 1 times 0 is 0, plus 0 times 1 is 0. So the result there then, the product, will be 6 minus 1 is 5, 0 minus 1 is a negative 1, 3 plus 0 is 3, and 0 plus 0 is 0. So there's AB, which means that AB transpose, we just take the transpose of this 2 by 2 matrix, and we would take the first row, 5, negative 1, and make it the first column, 5, negative 1, and then the second row, 3, 0, becomes the second column, 3, 0, and there's AB transpose when we first take the product AB and then transpose it. What if, though, instead we do it the other way, this right-hand side way, and we find these two transposes individually? So if we first find B transpose, let's say that B transpose A transpose is equal to, we'll put B transpose here first. So looking at B here, that's going to be 3, 0, and then 1, 1. And then we multiply that by A transpose. Well, A transpose is going to be 2, negative 1, goes down the first column, and then 1, 0, goes down the second column. And so if we then find this 2 by 2 matrix, we'll do 3 times 1 is 6, 1 times a negative 1 is a negative 1, 6 and a negative 1 is 5, 3 times 1 is 3, 1 times 0 is 0, 3 and 0 is 3, 0 times 2 is 0, 1 and negative 1 is a negative 1, 0 and negative 1 is negative 1, and then 0 times 1 is 0, 1 times 0 is 0, and 0 plus 0 is 0. And so notice how we get the same value either way. If we calculate the product AB and then take its transpose, we get 5, 3, negative 1, 0. If we find the transposes of A and B individually, A transpose and B transpose, and then we multiply B transpose by A transpose, we get the same matrix 5, 3, negative 1, 0. So that sort of proves to us this formula for the transpose of a product. And then we want to go ahead and talk about sums. And this is another formula that we can use when we want to manipulate transposes. So this formula tells us that, again, if we have two matrices, A and B, if we take their sum, so we add the matrices together, which obviously they have to have the same dimensions in order for us to be able to add them. And then we have that resulting matrix, that sum, that's going to be a matrix. If we take the transpose of that matrix, that's the same thing as adding together the transpose of A and the transpose of B. So if we just transpose the matrices individually and then add those results, we get the same thing as if we first take the sum and then transpose the sum. So to show that that's true, we could use these same matrices A and B. We already know their transposes, A transpose and B transpose. We said that this was B transpose and this was A transpose. So if we add those together to get the right-hand side here of this formula, we get A transpose plus B transpose is equal to, and if we add them, we get 3 plus 2 is 5, 1 plus 1 is 2, 0 plus negative 1 is a negative 1, and 1 plus 0 is 1. So that's the sum of the individual transposes. But if we go the other way and find the sum first, let's look at the sum here, A plus B. We have A and B here, so if we take their sum, 2 plus 3 is 5, negative 1 plus 0 is a negative 1, 1 plus 1 is 2, and 0 plus 1 is 1. So that's the sum. And then if we transpose that, so let's just call this now A plus B transpose, and ignore this for a second. A plus B transpose will be, when we transpose this, 5, negative 1 will become the first column, and 2, 1 will become the second column. And so we have 5, 2, negative 1, 1, which is the same thing we got, 5, 2, negative 1, 1, when we took the transposes of the matrices individually and then found the sum of the results. So we can see that this formula does in fact work. And then the last thing we want to know is the transpose of an inverse matrix. So when we're talking about inverses, we want to know that if we take A transpose, we start with the matrix A and we take its transpose, and then we find the inverse of that transpose matrix, that's the same as starting with A, finding the inverse of A, and then taking the transpose of the inverse. So if we want to show that to ourselves, let's say that we're starting with this matrix A that we made up, 2, negative 1, 1, 0. If we first take its transpose, we're working on this left-hand side of this inverse formula. If we first take its transpose, we already know that we get A transpose down here, 2, 1, negative 1, 0. So that's A transpose. If we find its inverse, we can do that by putting the matrix into reduced row echelon form. So 2, 1, negative 1, 0. And we'll go ahead and augment that with the identity 1, 0, 0, 1. We'll use this method for finding the inverse of A transpose. If we go ahead and swap rows 1 and 2, we'll get negative 1, 0, and then 0, 1, 2, 1, 1, 0. Then if we multiply through the first row by a negative 1, we'll get 1, 0, 0, negative 1. And then in the second row, if we subtract 2 of this first row from the second row, we'll get 2 minus 2 times 1 is a 0. 1 minus 2 times 0 is a 1. 1 minus 2 times 0 is a 1. And 0 minus 2 times a negative 1 is 0 minus negative 2, or 0 plus 2. That's a 2. So then the inverse is this matrix here, 0, negative 1, 1, 2. So we can go ahead and say that A transpose inverse is equal to this matrix here, 0, negative 1, 1, 2. The question then is, do we get the same thing when we calculate the value of the right-hand side? So if we work first on finding A inverse, we know we're starting here with A, which is 2, negative 1, 1, 0. So let's go ahead and start with 2, negative 1, 1, 0, and we'll augment that with the identity. We'll use the same method to find the inverse. If we swap rows 1 and 2, we'll get 1, 0, and then 0, 1, 2, negative 1, 1, 0. Then if we subtract 2 of the first row from the second row, we'll get 2 minus 2 times 1 is a 0. We'll get negative 1 minus 2 times 0, that's still a negative 1. We'll get 1 minus 2 times 0, that's still a 1. And 0 minus 2 times 1 is 0 minus 2, or negative 2. And then the first row stays the same. And then we multiply through the second row by a negative 1 to make that into a positive 1. And we get 1, 0, and then 0, 1, 0, positive 1, negative 1, positive 2. So this is our resulting matrix here. But let's go ahead and make some room. We'll get rid of this, which we don't need, and then these values that we don't need. We just have A transpose inverse. But this, what we just found, this on the right-hand side here, this is A inverse. So we know A inverse is 0, 1, negative 1, 2. And if we transpose that, we get A inverse transpose, and that's going to be equal to 0, 1, the first row becomes the first column, 0, 1, and then negative 1, 2, the second row becomes the second column, negative 1, 2. And notice now that A transpose inverse and A inverse transpose are the same matrix, 0, negative 1, 1, 2 in both cases. So we were able to find the value on the left and right-hand side and prove that they were equal to one another. The good news too is that these formulas also work in higher dimensions. So if we have larger matrices, not just 2 by 2, but 3 by 3 matrices or 4 by 4 matrices, these formulas are going to hold. And if we use more matrices, these formulas are going to hold. So for example, for the product here, let's say A, B, and C were all 3 by 3 matrices. We could say that A, B, C transpose is the same thing as C transpose, B transpose, A transpose. And same thing here, if we had A, B, and C and they were all 3 by 3 matrices, A plus B plus C, that whole matrix transpose would be equal to A transpose plus B transpose plus C transpose. So those formulas are both going to hold. The inverse formula will hold as long as we have a square matrix, because remember, only square matrices are invertible. But as long as the matrix is square, the matrix can be any size, and this formula will hold as well.